Welcome to The Explainer. Today, we're diving into what is literally a multi-billion-dollar mystery, right at the absolute cutting edge of artificial intelligence. Right now, tech giants and researchers are pouring staggering amounts of money and computational power into training advanced large language models to reason better using reinforcement learning. But there is a massive problem. Sometimes, for seemingly no reason at all, these incredibly smart models suddenly and catastrophically fail during their post-training phase. They just collapse. So today we're going to look at the groundbreaking research that finally uncovers exactly why this happens and, more importantly, how to fix it.
So why do leading AI models suddenly collapse during training? It's a question that's been keeping AI developers awake at night for sure. Reinforcement learning is the secret sauce that gives modern LLMs their deep reasoning capabilities. It's what allows an AI to pause, think step by step, and solve really complex math or logic puzzles. But this post-training paradigm, it is dangerously unstable. When a training run collapses, we aren't just talking about a few hours lost. We're talking about a massive waste of incredibly expensive supercomputer time and resources. So what exactly is the invisible wall these models keep hitting?
Okay, let's dive into this. Imagine training an AI is kind of like sending a robot to navigate a really treacherous mountain pass. In traditional reinforcement learning, the robot is struggling on a totally suboptimal path. The model is trying to maximize its reward, basically trying to reach the summit, but it keeps taking wrong turns, falling off cliffs, or just getting stuck in endless loops. It completely lacks the right map to bridge the gap between how it learns in the lab and how it's actually going to operate out in the real world. To solve this mystery, here's our roadmap. We'll start with the AI training trap, move to the hidden discrepancy, and explore a counterintuitive discovery. Then we'll break down the DCMDP solution, see how it unlocks heterogeneous training, and finally look at the future of efficiency. All right, let's jump straight into section 1, the AI training trap. Billions lost to unpredictable collapses. While reinforcement learning is absolutely crucial for pushing the boundaries of what these models can actually do, the entire community is plagued by this persistent challenge. You can have a model humming along perfectly, improving its reasoning scores beautifully, and then suddenly, out of nowhere, the optimization just destabilizes. The model forgets how to generate coherent text, or its mathematical gradients literally explode. Up until now, fixing this meant relying on these highly labor-intensive bespoke optimizations that just try to patch myriad corner cases across hardware and software. But what if the problem wasn't actually a bug in the code, but a fundamental conflict in the environment itself? That brings us to section 2, the hidden discrepancy, a tale of two engines. This right here is our prime suspect. Researchers identified something they call train-inference discrepancy. Think of it like a tale of two engines. During reinforcement learning, the AI actually splits its time between acting like a student learning the material and acting like a test taker. But here's the major catch. The training policy and the inference policy are running on totally disparate underlying engines. It's like asking two robots to walk the exact same tightrope, but one is wearing heavy, precision-engineered magnetic boots and the other is just wearing cheap roller skates. Let's put these two worlds side by side. Over on the left side, you've got your training backend. It requires stringent numerical precision, usually a high-fidelity format like BF16, to accurately update the billions of parameters in the model. It's incredibly expensive and super resource-heavy. Then on the right side, you have the inference backend. In the real world, to actually generate text quickly for users, the model needs extreme throughput. It's highly resource-constrained and relies on low-cost, lower-precision chips. Because these two backends calculate things slightly differently, their mathematical behavior slowly drifts apart. The training engine starts rewarding actions that the inference engine literally cannot execute properly, and boom, the training collapses. So the obvious fix would just be to force them to match perfectly, right? Well, researchers tried that, which leads us to section 3, a counterintuitive discovery, the Goldilocks principle of AI optimization. It turns out forcing those two backends into perfect alignment actually ruins the AI's ability to learn. The researchers discovered what they call a discrepancy tolerance region. It's essentially the Goldilocks principle of AI optimization. If you impose aggressive penalties to make the training and inference policies absolutely identical, you completely stifle the model's exploration. It spends all its time worrying about tiny numerical differences instead of, actually learning how to solve the math problem. But if you let it run totally wild, it collapses. The secret here is that the model actually needs just a little bit of wiggle room to reach its peak performance. Now, what's really interesting about this slide is the clear bell curve mapping the AI's performance against that discrepancy constraint. Look way over to the far left. At zero discrepancy, the performance is actually at its absolute lowest.
But as the tolerance region expands slightly to the right, performance peaks sharply. The AI absolutely flourishes when it's allowed harmless, microscopic deviations. It gives it the flexibility to explore vast decision spaces safely. So, how exactly do we mathematically program this sweet spot into an AI? Section 4, the DCMD solution, building a dynamic leash. Researchers essentially rewired the entire learning setup into what they call a discrepancy-constrained Markov decision process, or DCMDP. Instead of just checking for errors at the very end of a long sentence, it looks at the absolute probability difference at the token level, literally analyzing it word by word. To manage this, they introduced a Lagrangian multiplier. Basically, think of this as a dynamic leash. When the AI is exploring safely inside that tolerance zone we just talked about, the leash goes completely slack. The process gracefully degenerates into pure reward maximization. But the absolute second the AI wanders too far and the train-inference discrepancy gets dangerously high, that leash pulls taut, gently guiding the policy back to safety without micromanaging it. And this brilliantly illustrates how that dynamic leash actually works in practice. Look at the two robots now. The high-fidelity training policy is acting as a guide, continuously passing synchronized parameters to the inference policy. By injecting this real-time token-level discrepancy awareness, the training policy actively perceives the mismatch and initiates self-correction on the fly. They're successfully navigating the optimal path up the mountain together, rather than blindly wandering off two different cliffs. Which brings us to why this mathematical breakthrough is such a game-changer for the industry. Section 5, heterogeneous training unlocked, bridging the hardware gap. So this framework effectively treats the hardware infrastructure entirely as a black box. What that means for us is developers can now engage in a heterogeneous training paradigm. You can leverage the massive, high-cost infrastructure of a supercomputer using high-fidelity precision to train your model, but explicitly and safely align it for a low-cost, resource-constrained deployment environment, like the chips in our smartphones or everyday budget servers. It bridges the gap between the pristine lab and the messy real world completely automatically. And honestly, the data backs this up spectacularly. Just look at these results on complex mathematical reasoning benchmarks. On the Quen 3.8b model, the standard vanilla reinforcement learning setup scored an average of 67.3. But with our dynamic leash, the DCGRPO method, the score jumped up to a 71.0. And we see a very similar leap for the massive 30 billion parameter mixture of experts model, rising from 69.0 to nearly 72. By simply allowing the model to correct its own hardware discrepancies, the verifiable intelligence of the AI fundamentally increases. Which leads us to our final takeaway. Section 6, the future of efficiency. High-tier AI on budget hardware. The researchers sum it up perfectly in their paper, stating, "We enable a heterogeneous training paradigm, paving the way for highly promising, resource-efficient model deployments in the real world." I mean, that is the ultimate payoff right there. It's not just about stopping frustrating training crashes, it's about democratizing advanced AI. By solving this hidden discrepancy mathematically, developers don't have to spend months writing custom code for a dozen different hardware chips anymore. This breakthrough means the absolute highest tier of deep reasoning AI can now be trained reliably to run on highly constrained, budget-friendly hardware. The guardrails are finally in place. So I'll leave you with this to ponder. What are developers going to be able to build now that this invisible barrier to AI efficiency has been completely shattered? Thank you so much for joining me on this explainer, and keep exploring the incredible world of AI.